Hey everyone, my name is Victor Venegas, and I'll be covering matrix algebra, which is section 1.2, 1.3, and 2.3 in our textbook. So we'll start off by talking about what a matrix actually is. There are many definitions to what a matrix is, but I like the simple definition of it being just an array of numbers sorted by rows and columns. And in this class, we were introduced to them by looking at systems of equations with three variables and just taking the coefficients and putting them into a matrix. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have -1, -3, -5. And we just put them into a matrix and voila, we made our first matrix. As I said, they are sorted by rows and columns. So let's talk about what rows and columns actually are. So rows are usually represented by the letter M, and they're the number of lines that go horizontally. So here we have 1 row, 2 rows, 3 rows, and now columns are the number of lines that go vertically, which are represented by the letter N. So here we have 1, 2, 3, 4. So that makes our matrix a 3 by 4 matrix. And similar, we can look at more examples where we have 1 row, 2 rows, 3 rows, and 1 column, making our matrix a 3 by 1. And here we only have 1 row, but we have 3 columns. So this makes our matrix a 1 by 3. So now we will look at one way to solve for a matrix, which is by using reduced row echelon form. This requires us to use elementary row operations to reduce the matrix down to leading ones, or pivot points. You know you are done when your pivots or leading ones have zeros both and above them. In this example, we will start by looking at row 1, but in this case, we already have a leading one, so we can move on to row 2. In this case, it's a 4, and to get rid of this, we will need to subtract row 1 multiplied by 4 in order to cancel 1 and 4 out. And similarly, we do the same thing with row 3 by multiplying by 7 and subtracting it by row 3. So now we move on to our second matrix, which already has our first column down to 1, 0, 0. Now we can focus on the rest. So here we look at the second row, or the third row, sorry, to get 0. And to get 0 here, we multiply the second row by 2, which gives us -6. And then we subtract it, giving us +6, and that cancels the third row out. Now we do 0, and we do that to the other 2, and then this gives us -2. Now we are ready to move on to the next matrix. So now we have row 3, which has -2, and as we mentioned before, we need a leading 1. So to get that leading 1, we will multiply -2 by -1, -1/2, to give us the 1, and to start canceling the second row out, we will need to multiply the 3 by 1/3 in order to give us a 1. So now we are starting to get our leading ones. So we have 1, 1, 1. But now, as we mentioned before, we need to get rid of what is above and below our leading ones. So here we have 2, -7/2, and -1. So now to get rid of it in the first row, we multiply the second row by -2 and subtract that by the first row. So now in our next matrix, we have successfully isolated the second leading 1 because we have both a 0 above and below it. So now our job is to isolate the third row leading 1, and we do that similarly by multiplying the third row by 7/2 and adding it to row 2 because it is negative. So now that becomes 0, and similarly in the next step we do the same thing by multiplying by 6 and subtracting it by the first row. So now we have successfully put it in reduced row echelon form, and now it's our job to see how many solutions this has. Does it have one solution, infinite solutions, or no solution? In this case, it's a obvious tell because the last row is contradictory. It says 0. As we mentioned before, the line is equal to the equal sign. So now it's 0 equals 1, which doesn't make any sense and gives us no solution. So you can do more with matrices than just solve for them. You can also add and multiply, which we will see in the next step. But adding is pretty straightforward. The only rule here is that each matrix must have the same number of rows and columns. So here, in this example, we'll look at a 2x2 matrix, which is pretty straightforward. We just add each corresponding element to each other. So here it's 1 plus 5, which is equal to 6, 2 plus 6, 8, 3 plus 7, 10, and 4 plus 8 is 12. So now you see why you need the rows and columns to equal to each other, because if this were to be a 2x3, this would not work, obviously, because you have nothing to add corresponding element to. So multiplying matrices requires a bit more thinking, but it's still pretty straightforward. Multiplying requires you to have the same number of columns in the first matrix as the same number of rows in the second matrix for you to multiply them. So in this example, we meet the requirements, so we can start multiplying. So to start multiplying, you take the first row, you take the row in the first matrix and multiply it by the first column in the second matrix. So here we take 3, multiply it by 4, and we take 1, multiply it by 2, and then take 4 and multiply it by 6. Now we're ready to move on to the second column, and that gives us 3 times 3, 1 times 5, and then 4 by 8. So now we can add each column in their respective order. So all of this equals 38, and the second column gives us 46. And what I didn't mention before was the number of rows in the first matrix and the number of columns in the second matrix will give us the dimensions of our new matrix for our answer. So here we can see it's a 1x3 and a 3x2. So once we get rid of the 3's, we have a 1x2 matrix, which is also the matrix of our answer. So in this case, order does matter because you wouldn't be able to multiply it if A and B were switched, just because the columns and the rows would not equal each other as they do now. So that is all. Thank you very much for watching, and have a good night.